has been more shutdowns during since afternoon, so it could happen again. So this morning we have a few shutdowns here. Everything went black, and so we will take a couple of minutes to restart the machines and put everything back in place. So just in case that something like that happens, just wait for a couple of minutes. I just need to restart the machine. It takes like 2 minutes. And entering Zoom and all of that. So if you see that my connection suddenly falls, it's just that I got another shutdown here where I am. So all the materials are here. Let me see. Put it here. So right here, I think this is one way of getting. Let's see. Let's see if I can get it right. I think it works. And, so I will copy here command. For the materials are right there, are here in files. So today we'll be talking about OpenACC and CUDA. But before that, let's recapitulate really quickly what we mentioned yesterday about paragraph. So the idea is that most of that we do so Fortran is basically for scientific computing, and modern scientific computing is always attached to parallelization somehow. So we mentioned what we did this, what we went into parallel programming, and here yesterday I showed you a few options for parallel programming. This one that is part of the language now since 2018 or 2008, with some modification in 2018, Fortran co-arrays. So it has been around for more than 10 years now. So with this idea of images, where each image receives a different number, and with that number, you can redirect operations and effectively work in parallel. Okay, are you able to see my screen? I got a message saying that, like, blink or something. Daniel, are you able to see my desktop? I got a message here, weird message here. Okay. So now another option, and we explored this option yesterday. It's called OpenMP, originally created for dealing with multi-core processors like the LAS. But at some point, became clear that we need to do something about the emerging accelerators. And GPUs are the most prominent examples of that today, GPUs. So OpenACC inherit many of the ideas from OpenMP, but now target for a wider scope of using GPUs or basically any kind of accelerator, not necessarily GPUs. So with OpenACC, you program, you make some declarations for something that will go parallel. It could run on the GPU. It could run on multi-cores. So it's general. It could run in something else if the driver or the capability is inserted in the compiler for running on an alternative device. The difference between this core, the CPU core, and the GPU machine is that those devices are separate, are out on the main board, and they have their own memory. So there is something called the device memory that belongs to the GPU. It's a high bandwidth memory and not so large compared with the amount of memory that we have on the CPU, close to the CPU. So here on the main board, for example, on a typical node on our cluster, we have 96 gigabytes of RAM. Here, this is a relatively high-end GPU card. It has 24 gigabytes of RAM in memory. On a normal, more consumer-like product, like those GPU cards, NVIDIA GPU cards for gamers, they typically have 8 gigabytes maximum for storing textures, for storing all the elements that are required for the game. But those are more targeted for actual computation, so they have large memory capabilities, and they have some extra chips specializing on computation, like tensor chips, things like that. So we will be talking today about this kind of computation, computations that will be targeting this kind of devices. By the way, most of our compute nodes we have are these models, RTX 6000, with the memory shown there. So they have this number of CUDA cores. That's the terminology for NVIDIA, CUDA cores. A CUDA core is different from a CPU core. So making the analogy of saying that we have 4,000 cores on a GPU card is not something that you can directly compare with the CPU cores. First, the CUDA cores, and we will see that when we will discuss a little bit about CUDA Fortran. Those are very like entities. They just run under the command of some electronics here that run those threads, and they are basically doing exactly the same operation in clusters. So those CUDA cores doesn't work independently. Compared with the cores here on the CPU, they are actually independent. They can run a process independent from the others. So here they typically, you group them, and all of them are running exactly the same thing, are executing the same instructions, eventually on different data. So they are running on what is called a synced instruction, single instruction for multiple data. So it's different. So don't compare 4,000 CUDA cores with 24 cores. It could be misleading, that sort of comparison. So here I have, what I did yesterday was presenting basically the same code or the same algorithm for using coarrays, using OpenMP, and this one is the equivalent using OpenACC. So you will notice here this kind of instructions of directives here. They are very, very similar if you compare those with what we did here. They are remarkably similar. So the tag here is OpenMP, down is ACC, parallel do, and now we have parallel loop, and we declare a variable being private. Same thing with OpenMP. Here we are making a reduction with the sum for the variable pi. We'll collect all the values. And at the end, in Fortran, we need to open and close with directives the blocks that we will do, the sections of lines that we would like to cover. So same thing here, ACC and parallel loop. That is the general idea of with OpenACC, having this kind of directives, and we will see some of those in our examples. So all what it matters here is this is the section that is actually being parallelized. And how we compile that, you can compile it with GCC or Fortran using this argument here, F OpenACC, which is equivalent to -F OpenMP. So it follows a similar prescription, but we will prefer to use this one. So the NVIDIA Fortran compiler is much better, and it has direct support for the GPUs, and it's a much better solution. So when you are working with GPUs, you will probably use the NVIDIA compilers, either because for OpenACC, and we will see that it's the same thing for CUDA Fortran. Very similar idea. So let's move on to the section here. So this is OpenMP, and this one it's for OpenACC. So similar to OpenMP, we are using directives. Also, we can use an API, so functions for getting the number of the threads, getting internals about the execution. At that moment, the code will only work with enabling ACC, OpenACC. But if we are not using those functions, the API or the code should compile without any issue with a compiler that is not aware or is not compliant with OpenACC. No problem with that. So the idea always is that you take code, you have a code, or you have been working all the time with a code that is serial, and with minimal changes, we will move that code into a parallel code. That's the idea with this kind of approach. Minimal changes to the original code. People have developed their own codes for many years, and be involved in a large re-engineering is something that is not always desirable. So it could be costly and all that. So we will be using the NVIDIA compilers, NV Fortran. The general schema here for OpenACC directives is having a directive like parallel and having a set of clauses like private. Those are called clauses. And this is an ACC construct. If you want to use the API, is in Fortran is loading the module OpenACC. Remember that yesterday we did something like that. The OpenMP lib will do the equivalent the equivalent idea there. So now let's start with something very, very simple. We have this code. So here we have a module. Let's see this. We have a module here. This module has one subroutine here. This subroutine. This subroutine is doing one operation here, and it's an exponent, sinus. So it's doing something that it's still simple, but I tried to put some numerical effort on what is happening here. So it's something that, imagine that we require some parallelization for getting out some extra performance of this execution. So we are cycling this with a parallel loop, an M parallel loop, and this loop here with parallelize. Same thing as we mentioned yesterday for OpenMP. We can do this because this loop here doesn't have any data dependencies. So everything that is happening with B is from A, and we are not crossing data from previous, from other values of B. We are not using B minus 1, I minus 1 or something like that. That will break our code and will prevent us from parallelizing this. So we know that we don't have any data dependency. Same thing for as OpenMP, there is an implicit barrier here. So when this is done, if something is happening after that, we know that all the execution is complete. In this case, this section here, this loop here, could take place entirely on a GPU. And I mentioned that on a GPU, see if I can go quickly to this. On a GPU, there is a separate memory. We have 24 gigabytes of memory there. So it's a separate device. So here is doing far more than compared with what we did yesterday. Here, this call to ACC is actually moving data from the CPU, from the memory, from the RAM, the CPU RAM memory, into the device memory, doing the operation. So it's copying A, it's copying B, it's storing or doing all that operation, storing B and returning B and copying B back to the CPU. All that is happening. The OpenACC web page is not published. Let's see. Why? Let me check that. Let me check. Maybe I forgot. Oh yeah, you don't see this here on here. It's here. It's, let's say. So this is the web page. We just attach here. So I forgot to put it on here on the workshop. The link. See here. Can you see this, Blake?
Yeah, I can see this. So could you copy this one to the? Okay, thank you.
Can you see there? Blake?
Yeah. Thank you. Yeah. Now I can access. Thank you.
Okay. Not with the underscore, but with the dash. Okay. Oh, okay. So yeah, it was actually my mistake. I was creating those links here for every single section, but I forgot to put those for today. So so let's continue here. Oh yes, I don't have sound here, and if I put sound, I will get feedback. So that's why Let me see if I can do something about it so I can hear you. Let me see.
Can you hear me now?
Or not? Or is okay? I just connect my cell phone, so. But I don't want to have feedback here. Not feedback.
Okay. Could you?
Daniel, can you talk or say something to see if I can hear you?
Could you hear me now? Hey.
Here. Not sure if this is actually working.
Yeah. Okay.
I'm not sure that this is actually production. So here we have a module, and in this module we have some loop that we would like to parallelize with OpenACC. By the way, you can put here on top of this also OpenMP directive. So you can mix OpenACC and OpenMP, and it depends on how you compile it. You can enable OpenMP or enable OpenACC. So those things are not exclusive. Yeah. Okay. Yeah. So now here inside the program, which is using the module. So here I'm using the module. This program is using this module. I have another ACC loop that is initializing the array. What I'm doing actually is basically doing the opposite here. So I'm initializing with some value, and I'm changing that inside. So here I am calling the process, and that will execute this. The answer. So let me see if with this example 001 is files open GCC. So it's this one. Is this code here? So let's compile it. Module, I will purge modules here. So first, module load blank NVIDIA. This one. If I compile it this way, even if I put this and info equal all, it will compile, it will execute, it will initialize the array. It takes a while. I think that put a large value for here for n, so it will take a while if you are not parallelizing this. So actually I will do it differently. I will time this way because it takes, I think, almost a minute to get it. And after that, I will move into a GPU machine And you can do that. I will just take one of those GPU machines, and we have, how many of you are here today? I think you can request one GPU. So you can follow this if you want. You can request one GPU machine and execute this from the example. So it took 27 seconds. Yeah. So now that's what it takes. Now the next step will be to request use one machine, one GPU machine. So notice that which are the queues that we have. Only this machine, okay, this queue offers GPUs, but this one is just for non-interactive execution. This is the queue for interactive execution. This is actually the queue that we will be using. And this one is exclusively for the chemistry department. And I don't know if there is any other for GPU. So I am requesting one node, let's say 8 cores, and one GPU on the queue community GPU interact. Okay, relatively quickly. So you can try, you will take eventually this machine, a couple of you can take this machine. I am just requesting one, and this machine has 3 GPUs, and I think the queue for GPUs is relatively, yeah, it's okay. You will get it if you request the GPU node. So first thing, how you check that you got the GPU? NVIDIA SMI. Okay. So now you see I have a Quadro P1000, P6000. So I can see one GPU core here. The machine that has 3, but I'm only able to see one, and no process is running on this machine right now. So I will go for the materials, model Fortran, files, open ACC, and we are working on this one, 01. So we will compile this again. Module load and NVIDIA ACC and MV Fortran now with ACC and info all example 01. So let's read this. This is generating code. They mentioned Tesla code, so that it means it's going to parallelize using the GPU. Here is the first block, the first parallel block here. They mention here there is an implicit copy in for A. A is an input. So if you go here, let me see, let's review why we have that. A, B is something that will go in the output. It will realize that B is not important. B is not important. As an input, it's not important, because what this section here is doing is just taking A. So we need A on the device, on the GPU. It will do something with that. It will write that on B, and we need to copy back B. So that is what is mentioning here. It's doing a copy in for A, so it's copying A into the device. And copy out means copying from the device, from the GPU, all the array for B. And that is what is happening here inside the subroutine process. What is happening here, this is for the initialization of the array. there is an implicit copy out because there is no need to have anything on A before. Is copying, is making this big array and copy that out back to the CPU memory. So those elements are happening here implicitly. So now we will run this with time. So before it took like 27 seconds. Now it takes 3 seconds to do the same thing. So now you can see how much you accelerate this kind of thing. This is a very, very simple thing. We are just initializing one array, doing some operation, and returning that. But it's still, we got a huge improvement in performance that just by parallelizing. So let's review a few elements. We don't have a lot of time for going in reviewing all the possibilities on OpenECC, but the essential is the loops and the data movement. That is something new compared with OpenMP. So here are the instructions. So how you request one GPU, so you can execute it, and you can go and copy this and go and check this code and compile it yourself and do your own timing, explore what happens if you make larger or smaller arrays. This is something that you can do. It's right here. So I put all that inside files for the workshop. And there is something else that you can here, which is a good thing when you are compiling this. If you execute this again, it will give you a timing, which is really nice for profiling about the amount of time that the GPU spent on the different, in general, the process that took place there. So all that you have to do was declaring this PGI ACC timing, time equal 1, recompile and re-execute, and you will see all this. So when the code is executes, it enters here on this region. It took some time, this time, on the device, and here the transfer of data. And notice that this, I think that mentioned here, this timing is in microseconds. So the timing the time that it took to process the data compared with the time that it took to copy the data. And this is the important thing. Copying the data back in and out the GPU is far more expensive than the actual processing that is taking place. So you didn't notice that much because in the case of the serial execution, everything was put in a shell and all that. But now this one is a problem. It's taking 325 microseconds compared for something that takes just 20 seconds for execute. So same thing for the copy back. So it takes a significant amount of time, the copying in and out of the device. And this is something that we need to take care of in a minute, and we will do that. Something like this happens. So here, the initialization, that is what we did first here. It took 14 microseconds here for executing this, but 300 microseconds for copying the data back, the array A here. So copying this array back took 1/3 of a second. So This is heavy. Also because the size of the arrays is large. So all copying all that memory takes some extra time. So you will see this if you execute. This is how you can execute this. We did it when I execute this, when I was preparing this material. It took pretty much the same 27 seconds for the serial execution. And now you can re-execute this here, and you will see this it's taking like 4 seconds for this. So now let's explore one example here. This one is example, I forgot to put it. It's example number 2, I think, the Saxby, yes. Another example where we have something similar. We have a loop here, an initialization loop here for a much larger case. So we are initializing a couple of arrays, and here we are doing the computation here and calling the Saxby. So by the way, Saxby here means single precision, a number and a scalar times an array plus another array. So that's what we are doing here. So let's compile it and see what we can see. Now we have 3 sections here. This section inside the module, this section here, initialization section. Here we have another section, but notice that now we are reading why it's needed for writing why. So you will see extra messages here when we compile this. So here in the Fortran, ACC and info deform all. So look at this. We are copying in this, but also we are copying in inside and up and coming back one here. And something like this is happening here. Why? It's copying inside into the device and copying back from the device. And not for the initialization, it's just copying out. So let's execute this code on. And now a lot of the time here in this execution is actually taking place just for the movement of the data, just moving data in and out the device. By the way, what we have are people in NVIDIA realize that moving data in and out the GPU is something that is critical. That's why they have different versions of GPU cards. So those that go into a PCI Express, like those that I show you in the image, but they also have something that is like a grid is the actual GPU inserted on the main board on a specific socket. So that accelerates, I think it's like 10 times the speed of moving data. And for some cases, that is important. Notice here again, 77 seconds for the actual calculation compared with more than 1 second for the moving of the data. So now we are moving in and out, so it's double the time. And something here for the copy out. So you can see most of the time here is spent on moving the data. So now we will see an example here where we are taking one case, one good example, that is the Laplace solver. So this is basically simulating a 2-dimensional plate where we have set some temperatures on the borders, and we are simulating how that the temperature dissipate on the entire plate. So it's slightly more complex, but this is the perfect example. I couldn't find anything better to demonstrate this in a short code. And the reason for that is because we are doing this interactively. So let's review. This is the serial version of the code. So we start with this one. We have a certain array. Here, what is the size of the array? Here, 1000 times 12,000. And here we are initializing the temperature. No, here we are, what is the initialization? It's an entire separate routine here that initializes the array. It puts everything, the temperature is 0 everywhere, except for the last column and last row that set the temperature, fix the temperature in 100, I think. Yes, it fixed the temperature here. And here is where we are doing the iteration. So what we are doing is 1/4 and the average of all the neighbors in the grid. So now we see that we have some dependencies here. So for computing one array, we need the neighbors, but all of them for the same time. So we are working on this temperature based on the previous temperature. So at least those are different arrays. There are no data dependencies with that. But still, we have this double loop here that is making this average for the entire grid. Now, after doing that, we are replacing the values of temperature last with the values that we compute for temperature. So this is another double loop where we are updating this. This is just because it's simple to do this way, and an alternative to that could be using pointers, but that's another thing. That's another. So here we are not using pointers or things like that. We are just updating the array entirely from the previous array. And from time to time, we are looking into the temperature, what is going on, and tracking this temperature is right here, I think. Okay, where basically we are computing all the values here on the average. So let's see what else is happening here. Okay. And here there's some timings. So let's start with this code. Let's start with the serial version of this. It's right here is called Laplace 00. So Laplace 00 here. So this is the code that I was using. Let's compile it. Let's see. I think it, let me see what it's doing. It takes more than a minute. Oh, no, 16 seconds. Okay, good machine. So this is the number of iterations that it did. We were just checking every 100 iterations here. And this is the value of the temperature that we got at the end. And this is the total time. Now let's see what we can do for the first iteration of inserting this code with OpenACC. So it's right here. So we can see, okay, maybe we can just insert those things here. Kernels, we parallelized, we will do this in parallel. We will put another one here. So we have some block here, and that's it. That's all that we did. We put these ACC kernels, which will parallelize this. Let's see what happens. Now we would like to compile this with OpenACC. Well, I will actually info. So one copy in here, one copy here, copy in temperature, copy back temperature, copy in and out temperature. The TSV copied also there. And here, one copy in, one copy out. I think this one is the update. This one is the update. 46. So let me see, 46. It should be an update. It should be this one. So for this one, we don't need to copy temperature last. We just need to copy into the device temperature and copy temperature last when it finished the loop. And so what happens with this? 4,000. It's not running much better than before. Actually, I think it will run even worse, I think. Because now we are copying all that data in and out, and that is changing the balance of the execution. It's making this more. So yes, it took 29 seconds. 29. So the solution for that, or the next iteration of this, so we realized that we did this, and now we are moving data into the GPU. The GPU is doing something, but we are penalized by the movement of all that data. Yeah. So now we go into the next iteration of this. We keep this ACC kernels here and here. But now we will be moving the data for the entire loop, for all those iterations. The data will be copied right from the beginning into the GPU, and we will be working on the data inside the GPU all the time. So this copy in and back will not longer be an issue. So this one, I think, is the next, number 2 here, and you will see what we have here. So we are copying this, we are creating this, so we are allocating all that memory in the GPU. In those 24 gigabytes we have there is where the data is being copied. And now you will see no more copy-ins, copy-backs here, except here. Okay, it's still copying BP, which is a minor problem because this is just one scalar. So there are I will not be concerned with that. Is running this loop here, this execution here, and this. We will understand better the meaning of all those cryptic message here about blocks, threads, and these when we explore CUDA Fortran. It will become slightly better, but this is an entire topic on CUDA, which is beyond what we can achieve on this kind of lessons. Programming in CUDA is another topic. So yeah, so notice that we reduce a lot this data movement, and that will change how we perform now on this. So now it took less than 1 second actually. So remember that we did here, we are copying all the data from the very beginning. It's in this loop. So all this loop here is entirely working with the data that is already on the GPU. However, we will see something that is not right, I think, is that we are losing some information here. So here now, when we are writing this, when we are calling this, tracking the progress here, the temperature is not updated in the CPU, because we are not copying all that data back to the CPU, only at the end. So we can fix something like that by the last iteration that we have here is updating the temperature. And so updating, copying the data back to the CPU only under some circumstances. So this copy and this copy and this source code and this source code is exactly the same, except that here in one particular point, every 100 iterations, we are updating the temperature. So we are copying the data back, but it's just happening every 100 iteration, not every single iteration. So we are going slightly slower on this one. We will have a copy back, but sometimes it's something that you can accept. You can live with it. 4,000. It will be, yeah, it's still under one second. But there is one data that is being copied here. So when I compile it, you will see here copy back and update here. So it's copying the data back. So this is like a slight introduction of a small introduction of how OpenACC works. There are also all the things, but the time is not enough for that. Same thing as we did yesterday for OpenMP, this with task. You can have that sort of functionality also on OpenACC, so you can have multiple threads or multiple GPU threads or accelerators working on different tasks. Same thing. So I think the best it could be to move into another brief introduction on a CUDA Fortran. So actually the best, it's after you see CUDA Fortran, you will come back and understand better what is happening here in OpenACC, all those messages related to thread blocks and things like that. So CUDA Fortran. So CUDA Fortran is not longer Fortran. So this is an extension, this is a superset of Fortran that modifies, add things to the language that are not part of the standard Fortran. Actually, CUDA Fortran is easier to program. It's easier to program in CUDA Fortran than it is with C CUDA. Because Fortran give you some nice features in the way the language was designed that are not present on C, so that facilitates some things. So the idea is that again we have, and this is specific for GPUs and is specific for NVIDIA GPUs. So CUDA is a technology that only works for NVIDIA GPU. Different from OpenACC that works on many other accelerators, like different brands of GPUs or different devices, not just GPUs. But this one is specific for NVIDIA. So the idea is pretty much to take advantage of those GPUs. Those GPUs have, you saw that we have like 4,000 cores, and something that we can check here with NVIDIA SMI and the big W. Not really sure if they tell you here the number of GPU. They tell you the memory here, but not the number of GPU cores. I don't think so. Yeah. So they have like 4,000 GPU cores, but the way those cores work is very different. They are not doing the same. They are not independent of each other. They work together, doing exactly the same operation in batches, in groups. And that will be evident in the way we will follow this small tutorial on it. So all that we did with OpenACC that became very, very automatic, now in CUDA is explicit. Now you need to move the data in and out the device. In Fortran CUDA, that is really, really simple compared with CUDA-C. But still, it's something that you have to do. Initialize data, allocate, all those things, and the execution on preparing the functions that run inside the GPU is something that now you have to do explicitly, compared with OpenACC that do all that stuff behind curtains. So we will start with this small example in CUDA. So now we are here in CUDA. So what I'm showing you is this example here, Saxby. By the way, notice that another thing to notice is that in CUDA Fortran, if you want to compile easily, it's not the only way, but one way of compiling this to indicate the compiler that what you have is CUDA Fortran, no Fortran 90 or Fortran code, is by changing the extension of the file into CUF. So that's one thing that you will notice. So that means that the VI is no longer putting highlights on my code because it's not recognizing the extension. So what are we doing here? We have a module here. This module has one subroutine here, but it has something weird here that it doesn't belong to the language. We will see this, because this is not a standard Fortran. We will see here some things that we will explain in a minute that are also not part of the language. They look like asking for the components of a DRI type. That's how they look like. But there is nothing here indicating those elements. And here we have the main program. Main program is basically Fortran, except for a few things. So we are loading this. We are using this module here. Yes. So in and out means from the CPU memory, so the RAM, into the memory that is inside the GPU, and copy out is from that device back to the RAM, the CPU RAM. So the memory that the CPU is able to see directly. By the way, if you are using for this, there is a nice thing now that is called manage. We will try to compile this with managed memory. In that case, they make way of making transparent that the memory is inside or outside the device. And it looks like the CPU is able to address, is able to see the memory. It's called managed memory, and it's something that you can enable when you are compiling this. We will see that in a minute. We will try to see if we can make the experiment about moving data with managed memory and the kind of things that change with it. So what is not Fortran here? This is definitely not Fortran. So this is one of the big things that change when you are compiling with CUDA Fortran. This 3 less than, 3 greater than, this couple of values here that are exotic, and the name of the function or the name of the subroutine here with those extra elements here, and after some arguments here. So this is not part of the language, definitely. This dimension 3, this is, you know, we learned this from the first day that this is a derived type. This derived type was defined here in CUDA Fortran. So if a code relies on CUDA, this is CUDA Fortran, you need to load this module, CUDA 4. It will define this dim3, which is actually like a 3-dimensional, so it is a derived type with 3 values, x, y, and z. And those values are important for managing the threads and the thread blocks inside the GPU. So let's see what we have. So new things, we are using this module, the module that we create, and the CUDA 4. This is part of the CUDA 4, so it's inside. Now we have more arrays here. So we have this couple of arrays that we define with a fixed size, but they could be allocatable, they could be dynamic. But now we have an attribute that this is not part of it's not part of Fortran language. This is not of those attributes that we saw yesterday. The first day, like pointer, allocatable, parameter, or the attribute that we saw yesterday, answering the question about saving arrays. So this is a new attribute that is not part of the language device. So the idea with that attribute is that those arrays here are created inside the device memory. That's how you declare those. Here, those are regular arrays and a scalar here that reside on normal memory on inside the RAM. So we now need to make that separation. We now need to duplicate that because the GPU is not able to see directly the RAM memory, and the RAM memory, the CPU is not able to see directly the GPU memory. The good thing is that if you know CUDA C, you need to actually call some functions to copy in and copy out the memory. So now in Fortran is as simple as copy like this. You are just making a statement, and all that memory is copying from the CPU, from the memory, the RAM, into the GPU. So copying the contents of that array inside the other side on the device. And same thing when you are copying back. So it's just one line, no functions, nothing fancy. The movement of the data became much clean in Fortran compared with C. And now this thing, SAXP, the function, this couple of things. So those, the way GPU arranged all those CUDA cores. It's very particular. So now we are going and trying to talk with the GPU and making an arrangement on how the different cores will be aggregated and how they will work together. They are not independent. So those are multiple cores that will work together, and they will execute as a thread group. And they are arranged in the CUDA specification. They are arranged in 3 dimensions. So you declare grids, and here we have the grid here. This is a grid. What's the grid here? Here, the grid. We are defining the grid here with a certain number of thread blocks. And one thread block is an aggregation of threads that will be executed together. So all of them will execute the same instruction at the same time, eventually on different data. So what we are doing here, we are able to do it in 3 dimensions, but we don't need it because we are working here in just one array. So we are making groups of 256 threads. So this 256 is a thread block. And now the question is how many thread blocks we need to cover the entire array. Just for this case, I made this on purpose exactly identical, but the code will work even if you change this. There is something here, we will see this, that we need just to go beyond what we need to cover the array. So all the elements, but not all, but eventually we need to stop before the array to prevent segmentation fault. So we will see that in a bit. That will become so. So the main message here is that we are aggregating 256 threads together, so they will execute as a group. And now the question is how many we need of those groups for processing the entire array. And it's basically the ceiling. So the next integer on the division of this. Remember that when we are dividing integers, we divide integers, we return an integer. So we are converting this n, that is an integer, into a real number. So the division will return a real number. And we are dividing this by this x, which is this 256. So in this particular case, and you can change it, and you can try the different value later, it will give you 4,000. So I did it to be precise, but it doesn't need to be that way. So I will need a grid of 4,000 thread blocks. And that is the information that I'm sending here into this function. Notice that this is far more complicated than the normal Fortran execution. Now, the arguments are the arrays that are inside the device. Everything, this function is meant to be executed in the device. And you say that when you declare that with attributes global, it means this way, that this routine here, this subroutine, can execute on the device or on the CPU. It's made for both. It will actually, the code when you compile will generate 2 different copies or 2 different versions of this function, one for the CPU, one for the GPU. So that is the meaning of global here. I think that you can also put a device and it will be just for the device, but global is okay. And now what I'm doing here is printing some elements so you will see how this works. So I'm here and initializing those arrays with random numbers. So I don't know exactly what I will get on every single iteration. So now how we compile this? If you set the extension for CUF, it will work. We'll compile this. Let me see if I put this. Not much. The reduction is. And now I can execute this. It's extremely fast. So I am creating an array, 1 million elements. So I have a grid of 4,000 thread blocks in one direction, one and one. So this is on one. I address those with just one index, the first index here, the X index. Each of those thread blocks has 256 threads. Now, this was the constant that I select randomly, and as all that array or random numbers from 0 to 1. So in average, they are close to 0.5. So this is a number that I expect. And now we are increasing, we are running this SAC speed. So we are increasing those values by this value here. So we are raising actually the average. So that's why you get will not be the same every single time that you execute this, but it will will be the same. Oh yes, because I never changed the seed for the random number generator, so it's generating the same random numbers. So that's why I never initialize. I just don't pay attention. So it's always the same collection. So that's it. The code runs there. Let's see here. So that's what it's doing here. So we are calling the function. And here we are deciding the size of the thread block. Here we are using that to define how many elements we are computing. And here is the code. So let's go now into the device code. This subroutine. What exactly are we doing there? We need this element here to get an index on which is the element. Notice that there is not a loop here. This is not all the threads will receive this execution. They will execute the same subroutine. The only thing is they will have different values for this, and not for this. They will get this block dimension. They will get 4,000, but this value will be different, and this value. So they will belong to a different block ID, one of those 4,000, and they will have a different thread ID in the thread block, from 1 to 256. Another difference compared with C is that here you need to make the correction, because in C they naturally start with 0. Here you need to introduce this to shift the value to get the right index. And here I am checking, and that's why I'm not constrained to having just exactly an array here. So I don't need to make this array exactly divisible by 256. If this index is still smaller than the size of the array, so if I am still able to address the array, I can execute this. Otherwise, if I don't put this, if I don't add this conditional, I will get a segmentation fault. I will be basically addressing beyond the length of the array, and that will be a bug. So that's what we are doing here. This index here is using the block dimension, so we have the 4,000, and here we will get one value from 1 to 4,000, so we need to shift it, and here we will get a value from 1 to 256, so we can use this to address the elements in the array. So here I code a note that in CUDA-C, those arrays start from 1. So it's slightly different. So those are the minimal difference compared with CUDA-C, but everything else is pretty much the same. How we compile it, I already compiled it for you. It's you have the extension, no matter if you put it lowercase or uppercase, it will identify that. And only you can compile only with the NVIDIA compiler. So this is specific for NVIDIA. You compile it this way, you get the executable, you execute this, and you will get something really, really similar to this output here. So now that you execute now, you got an experience on how this works with CUDA, you get an appreciation on how easy it is to avoid this and working with OpenACC. We avoided a lot of manipulations with threads, designing thread blocks, all that is happening. And when we did this, let me see if I still have that. When I execute this here, see, they mention the thread blocks used here. So they were using 128 here. So they have this message here. Exactly comes from there, comes from CUDA. Those are automatic decisions that OpenACC takes, that you have to do it explicitly here with CUDA, with CUDA Force. So that is all that I have for today for an OpenACC. We actually finished on schedule. Tomorrow we will move into something completely different. We will talk about MPI. It's a completely different way of parallel programming with Fortran, and it will be very similar to the way you program C, but the routines have some extra argument, but that we will see. We will see that tomorrow. So thank you very much. And if you want to explore and you have questions, you can execute those codes. And actually, I have some extra there. If you want to open to, I think I put some extra here. Oh no, I will put some extra examples here if you want to explore them. They are here. I will commit those in a minute. That's it. Okay. Okay. Thank you very much. If you have questions related to this or what we talked yesterday about Fortran, it could be something general about Fortran. I have no problem to answer. So this week is dedicated to Fortran, so I will be answering any question specific that you will have about those things if you want.